Hello, everyone. Welcome back to Faxpire. Today we're diving into something so mind-bending, so wildly expensive, and so downright bizarre that it makes gold, diamonds, and even the rarest truffles look like pocket change. We're talking about antimatter, the most expensive material on planet Earth. Now I know what you're thinking. What even is antimatter, and why should I care? Buckle up, because by the end of this journey, you're going to be obsessed with this stuff. It's the ultimate cosmic enigma. A substance that could power starships, unravel the universe's deepest secrets, or, get this, wipe out entire cities in the blink of an eye. And here's the kicker. It costs about $62 trillion per gram. Yeah, you heard that right, trillion with a T. So, let's unpack this wild ride together, starting with what antimatter actually is, how it's made, why it's so pricey, and why it's got scientists, dreamers, and even conspiracy theorists losing their minds. First things first, antimatter isn't some sci-fi gimmick cooked up by Hollywood. It's real, and it's the mirror image of everything you see around you. Picture this. Every particle in the universe, like electrons, protons, neutrons, has an opposite, an antimatter twin. For electrons, there's positrons. For protons, antiprotons. These twins have the same mass but opposite charges. So a positron is like an electron's evil doppelganger, with a positive charge instead of a negative one. Sounds cool, right? But here's where it gets wild. When matter and antimatter meet, they don't just shake hands and call it a day. They annihilate each other. Poof, gone. In that split-second collision, they convert all their mass into pure energy, following Einstein's famous E=mc² equation. This isn't some gentle fizzle, it's the most efficient energy release in the known universe. 100% of their mass becomes energy. Compare that to a nuclear bomb, where less than 1% of the mass turns into energy, and you start to see why antimatter is a big deal. Now let's put that into perspective. Imagine you've got a single gram of antimatter, about the weight of a paperclip. If it touched a gram of regular matter, the explosion would release energy equivalent to 43 kilotons of TNT. That's roughly 3 times the power of the Hiroshima bomb. From a paperclip. Let that sink in. This annihilation property is why antimatter is both insanely valuable and ridiculously dangerous. It's also why nobody's casually carrying it around in their backpack. But before we get into how it's made or why it's worth more than entire countries, let's rewind to how we even discovered this stuff. Because the story of antimatter's origin is a roller coaster of human curiosity and cosmic luck. Travel back to the late 1920s. A brilliant British physicist named Paul Dirac is scratching his head over equations that describe how particles like electrons behave. He's trying to blend quantum mechanics with Einstein's relativity, two mind-bending fields that don't play nice together. And then, boom, his math spits out something bizarre, a prediction that every particle should have an opposite with the same mass but a flipped charge. Dirac didn't set out to discover antimatter. He stumbled onto it because the numbers wouldn't lie. At first, people thought he was nuts. Negative energy, mirror particles. It sounded like something out of a fever dream. But a few years later, in 1932, an American physicist named Carl Anderson was studying cosmic rays, high-energy particles zipping in from space, when he spotted something weird in his cloud chamber. There it was, a particle moving like an electron, but curving the wrong way in a magnetic field. It was a positron, the first antimatter particle ever detected. Dirac's wild theory wasn't just right, it had rewritten reality. This discovery kicked off a scientific treasure hunt. If antimatter was real, where was it hiding? Why wasn't the universe blowing itself up with matter-antimatter collisions? That's when we hit one of the biggest mysteries in cosmology, the Great Antimatter Vanish Act. See, when the universe kicked off with the Big Bang, nearly 14 billion years ago, it should have churned out equal amounts of matter and antimatter. And if that's true, they should have annihilated each other completely, leaving nothing behind but a sea of energy. No stars, no planets, no us. Yet here we are, made of matter in a universe that's overwhelmingly matter-dominated. Scientists call this the baryon asymmetry problem, and it's still unsolved. One theory is that for every billion antimatter particles, there were 1,000,000,001 matter particles, a tiny imbalance that left us with the leftovers. Another idea? Maybe antimatter got shunted off to some hidden corner of the cosmos, forming anti-galaxies we haven't spotted yet. Whatever happened, that missing antimatter is one of the reasons this stuff fascinates us. It's a clue to why we exist at all. So, antimatter's rare in nature, but it does pop up in tiny amounts. Cosmic rays smashing into Earth's atmosphere create positrons all the time. Even bananas, yep, those yellow snacks, emit positrons because of a radioactive isotope called potassium-40. Don't freak out, it's a minuscule amount and you'd need to eat billions of bananas to notice anything. Lightning storms can generate antimatter too, spitting out positrons during high-energy bursts. And out in space, the center of our galaxy churns out antimatter from intense processes like black hole activity. But here's the catch. These natural sources produce antimatter in fleeting, microscopic doses. If we want enough to study, or dream about using, it's not lying around waiting for us. We have to make it. And that's where the $62 trillion price tag comes in. Let's head to CERN, the European Organization for Nuclear Research, home of the Large Hadron Collider. This is ground zero for antimatter production. Picture a massive underground ring, 27 kilometers long, where particles are smashed together at near-light speeds. Scientists use these collisions to create antimatter particles like positrons and antiprotons. But it's not like they're churning out buckets of the stuff. To make a single antiproton, they fire protons into a metal target, generating a chaotic spray of particles. Then, using magnetic fields and electric traps, they sift through the mess to capture the antimatter bits. It's like fishing for a single goldfish in an ocean with a teaspoon. In 1995, CERN made history by creating the first antihydrogen atoms, pairing antiprotons with positrons, 9 of them to be exact. They lasted for a fraction of a second before annihilating with regular matter in the lab. 9 atoms might not sound impressive, but it was a breakthrough that took years of effort and millions of dollars. Now, let's talk numbers. Producing 1/1000th of a gram of antimatter, called a nanogram, takes CERN about $10 million in a year of work. Scale that up to a full gram, and you're looking at $10 trillion just for the energy and equipment, not counting the decades it'd take or the salaries of the brilliant minds involved. Some estimates bump that cost to $62 trillion when you factor in the global infrastructure needed. For comparison, the entire GDP of the United States is around $25 trillion a year. So a gram of antimatter costs more than 2 years of America's economic output. Why so expensive? It's not just the rarity. It's the insane precision and energy required to make and store it. Antimatter can't touch anything. A single speck hitting a container wall would trigger an explosion. So scientists use magnetic and electric fields to suspend it in a vacuum, like a sci-fi force field. That tech alone is a budget buster. But here's where it gets really juicy. What could we do with antimatter if money were no object? Let's start with energy. Remember that 100% mass-to-energy conversion? A teaspoon of antimatter could power the entire United States for a day. A gram could send a spacecraft to Mars in weeks instead of months. NASA's been dreaming about antimatter propulsion since the 1950s. The idea is simple. Mix antimatter with matter, channel the explosive energy out the back of a rocket, and zoom off at speeds chemical rockets can't touch. Some designs suggest a ship could hit 10% the speed of light, fast enough to reach nearby stars in a human lifetime. Imagine colonizing Proxima Centauri or sniffing out alien life, all thanks to this cosmic dynamite. Of course, there's a flip side. That same energy makes antimatter the ultimate weapon. A half gram could level a city. In the 1980s, the U.S. Air Force even studied antimatter bombs before realizing the cost and containment issues were impossible to crack. Thankfully, we're nowhere near producing enough to weaponize it. CERN's total output since they started, about 10 nanograms. You'd need 1,000,000 times more just to boil a cup of tea. Still, the idea of antimatter weapons has fueled sci-fi and conspiracy theories for decades. Some folks whisper that secret government labs are hoarding it, but there's zero evidence, and the physics says it's a pipe dream. Let's shift gears to something less apocalyptic: medicine. Antimatter's already saving lives, believe it or not. Ever heard of a PET scan? That's positron emission tomography. Doctors inject you with a tiny bit of radioactive sugar that emits positrons. When those positrons hit electrons in your body, they annihilate, releasing gamma rays that a scanner picks up to map your insides. It's antimatter helping us spot cancer, heart disease, and brain disorders. Millions of PET scans happen every year, and most patients have no clue they're harnessing the universe's weirdest stuff to stay alive. It's a rare case where antimatter's practical and doesn't cost trillions. Now let's zoom out to space. Antimatter could be the key to unlocking cosmic mysteries. Scientists at CERN's Alpha experiment are studying antihydrogen to see if it behaves exactly like regular hydrogen. Why? Because if there's even a tiny difference, say, in how it responds to gravity, it could explain that missing antimatter from the Big Bang. Get this, some theorists wonder if antimatter falls up instead of down. So far, tests show it falls normally, but the jury's still out. Meanwhile, out in the cosmos, the Alpha Magnetic Spectrometer on the International Space Station is hunting for antimatter signals from dark matter collisions or distant antistars. Finding a chunk of natural antimatter could rewrite everything we know about the universe's birth. But let's bring it back to Earth for a sec. Specifically to human psychology. Why are we so obsessed with antimatter? It's not just the science, it's the story. It's the ultimate underdog, rare, elusive, and misunderstood. It taps into our love of extremes, the most expensive, the most dangerous, the most powerful. It's a symbol of what we can achieve when we push the limits, like landing on the moon or splitting the atom. And yeah, it's a little terrifying, which only makes it more irresistible. Think about it, we're drawn to things that could destroy us, whether it's fire, the ocean, or this cosmic wild card. Antimatter's price tag isn't just about money, it's about the cost of chasing the unknown. Historically, that chase has had its quirks. In the 1960s, physicists at Brookhaven National Laboratory created the first antimatter nucleus, an antihelium core. It was a fleeting triumph, gone in a flash, but it proved we could build antimatter piece by piece. Fast forward to today, and we're trapping antimatter longer, up to 16 minutes in some experiments. Each step forward costs a fortune, but it's fueled by the same curiosity that drove Dirac to his equations, or Anderson to his cosmic rays. It's humanity betting big on a substance we barely understand. Let's explore nature for a moment. Antimatter isn't just a lab toy, it's tied to the wildest forces out there. Take pulsars, spinning neutron stars that blast out radiation. Some emit positrons, hinting at natural antimatter factories in space. Or consider the Van Allen belts, Earth's magnetic shields. They trap positrons from solar wind and cosmic rays, creating a faint antimatter halo around our planet. It's a reminder that antimatter isn't alien. It's woven into the fabric of reality, just out of reach. Technology-wise, the future's tantalizing. Beyond rockets and medicine, antimatter could spark an energy revolution. Imagine power plants running on micrograms of the stuff, outpacing solar, wind, and nuclear combined. The catch? We'd need to slash production costs by a factor of 1 billion. Some dreamers propose mining antimatter from space, say from Jupiter's magnetic field, which traps antiprotons. Others bet on quantum breakthroughs to synthesize it cheaper. Either way, it's a long shot, but the payoff could reshape civilization. So, where does that leave us? Antimatter's the ultimate paradox. A speck of it can heal you, a gram could kill you, and a pound, well, that'd take more money than exists on Earth. It's a bridge between the tiniest particles and the vastness of space, between our past and our wildest future. $62 trillion a gram sounds insane, but it's not just about the cost, it's about what it represents. A challenge, a mystery, a spark of human defiance against the limits of the possible. Next time you hear about antimatter, whether it's in a lab, a sci-fi flick, or a random banana fact, remember, it's not just the most expensive material on the planet, it's a window into everything we are and everything we could become. Thanks for sticking with me on this epic dive. If you loved it, hit that like button, subscribe, and let me know what mind-blowing topic you want next. Until then, keep looking up. And maybe don't try to buy any antimatter on eBay. See you soon.